So here's the back of a conventional speaker. You have a plus and a minus. You can either put bare wire underneath those once you unscrew them, or you can connect, for instance, dual banana jacks. So here's a block diagram of a conventional normal two-way speaker. You have the amplifier over here. Typically we show that with the symbol of a triangle. This is the input, this is the amplified output. I put it in a steel box, so I made this box gray, but the speaker I made a wooden box, so I made the wooden box brown. Anyway, the signal comes out of the amplifier. It leads to a short little wire to the outside of the cabinet to the binding posts. Then this is the length of wire across your living room traveling to where you place your speakers. It goes into the speaker cabinet. Another short piece of wire connects to a device called a crossover, which separates the high frequencies to the tweeter and the low frequencies to the woofer. This speaker has bi-wireable or bi-ampable binding posts. You have two sets. You can either bi-wire, meaning run two runs of wires to your single amplifier, or bi-amplify, which means use one amplifier for the high-frequency tweeter section and another amplifier for the low-frequency woofer section. This video is discussing bi-wiring. So with these supplied gold jumper straps removed from the speaker, you can connect separately for the highs and separately for the lows. So here are the two wires coming from the amp for the highs and the lows. I'm just playing a noise signal at the moment. This is what the highs sound like. This is what the lows sound like. Combine them together and you have full range noise. So the high and low frequency wires coming from your bi-wired speaker merge together at the amplifier posts. Just showing one channel of amplification to make this easy. You can either merge them at the binding posts themselves, or I've decided to merge them together on my dual banana jack. Or you can merge the two reds and blacks together onto single bananas. So with a normal speaker, you have just one wire, but with bi-wiring, you have two wires, bi-wires. You have one set of wires leading from the amplifier for the high-frequency input, leading ultimately to the tweeter, and then another set of wires for the low-frequency section leading to the woofer. The benefit is said to be that you keep the highs and the lows separated. As I mentioned earlier, bi-amping is a completely different topic from bi-wiring. You have two amps as well as two wires leading to the speaker. And then there are two varieties of bi-amping. Active bi-amping, the better kind, differentiates the high frequencies to one amp and the low frequencies to the other amp. Each amp has a lessened burden, so they actually can play slightly more loudly. But in consumer bi-amping, both amps have the full range signal coming in. This is more typically called passive bi-amping, and I don't recommend it. Now, on a bi-wireable speaker, you are not forced to bi-wire. You can also use a single wire by connecting the top to the bottom with the supplied jumper strap, or just called jumper. If you misplace it, you also can just use a short run of speaker wire. Now we're back into conventional mode, so you can connect to the bottom two or the top two, it doesn't matter, and you're connecting with one set of wires, conventional wiring. Again, either use bare wire into the holes at the bottom once you loosen these, or use bananas. If you had occasion to, you can connect two wires to these. For instance, I've taken two of this speaker wire, twisted two reds together, two blacks together, So here we're doing what's called dual wiring. This is not bi-wiring, this is dual wiring. The two wires are both running together in parallel to my single amplifier. And the advantage to this is I've reduced the resistance of the wire because you're using double the amount of strands compared to a single wire. So let's take a closer look at the difference between a normally wired speaker and a bi-wired speaker. First thing we're going to do is take a look at the crossover in the normally wired speaker. We're going to erase the gray box and look at what's on the inside of one of these crossover networks. Here it is. The wire signal comes in and it goes to two different parts. A high-pass filter, which filters out the lows, only the highs pass through to the tweeter, so that would be the treble, and a low-pass filter, which lets the lows pass through, and that goes to the woofer. That would be sort of the bass. So that's what the crossover does. Next thing we're going to do is we're going to make this diagram easier to read by erasing two things, the red wires and the binding posts. Now, you understand that whenever a signal comes into a cabinet, there will be binding posts, and you understand that all these wires are actually a plus and a minus, a red and a black. But I'm going to erase all of that to make the diagram easier to read. Now let's move on to the bi-wired speaker. What I've been showing you up to now is the simplistic version. I've just shown the signal coming straight in and going to the tweeter. But in truth, there are some electronics inside. So this is how it's often described in the owner's manuals. They make it seem like you're going straight to the tweeter and the woofer, but in truth, you do go through a high-pass filter and a low-pass filter, just like we did up above. So you are entering the cabinet with separate wires for the high-frequency network and for the low-frequency network, but you are still going through electronics. And the difference sonically is said to be better transparency. That's what the owner's manual to this speaker I show in the video claims. Other people say it has better clarity, better detail, better sound stage. Electrically, they sometimes say that the advantage is that the high and low frequencies don't contaminate each other, something that's sometimes called intermodulation distortion. Other people say that the back EMF or counter EMF. EMF stands for electromotive force. It's sort of an electrical signal that goes in reverse out of the woofer. And they say that the problem up here is that the back electromotive force accidentally gets into the tweeter, for example. And by keeping them separate, you help eliminate that problem. But let's take a closer look in this video what the real difference is between normal and bi-wiring. Okay, so this top diagram is our cheat sheet. This is conventional wiring. Now below it, I'm going to show you the mystery diagram, and you have to identify what is it. Is it single normal wiring or is it bi-wiring? Ready? Here we go. Okay, so here's our mystery diagram. You have to identify what is this speaker. I bet most of you said that it's a bi-wired speaker. Look at the cabinet of the speaker. All I'm doing is materializing it or making it disappear when I click my mouse button. When you see where the cabinet is, notice that this diagram is identical to this diagram. You have a wire coming in from the amp. It splits into two parts, just like it does here. It goes to a high-pass filter and a low-pass filter, and then off to the drivers. So in truth, bi-wiring is no different than normal wiring. The only distinction is whether the split in the crossover to go to the high-pass filter section and the low-pass filter occurs inside the wooden box or outside the wooden box. Are you still having trouble seeing that these are the same diagram? Here, let me modify this area just a little bit. So you see this would be the same diagram. This would be the same diagram. This would be the same diagram. This top diagram and this bottom diagram are exactly the same thing. Here's another way to look at it. Let me bring this cabinet back to the sort of normal size that you're expecting it to be. And now let's change this. So we started off from here, but that's really electrically no different than this. And it's really no different than this. This is sort of what a speaker that has the gold jumper straps attached looks like. It's no different than this. It's no different than this. It's no different than this. The electrical block diagram is exactly the same. So that's the trick to understanding why bi-wiring is pretty much bogus. There's no electrical difference. So for instance, those arguments that the counter electromotive force, or back EMF, is different between the two. The argument that the woofer is sending electrical energy that gets into the tweeter in this wiring diagram, but for some reason not in this diagram. That's absolutely bogus. But does that not happen here, or here, or here, or here, or here? Electrically, these are all the same thing. It just doesn't matter. So that argument about the electromotive force being, the back electromotive force or counter EMF being different is bogus. And then the idea of intermodulation distortion. As long as these wires all touch, it doesn't matter where they touch. The signal here coming out of the amp is exactly the same as the signal here, 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 and as the signal here. It's all one wire. In electrical block diagrams, one wire is assumed to be the same signal all the length. And if you need to hear this from another authority besides me, look at the block diagram for bi-wiring at Wikipedia. It's a little more simplistic than my diagram. For instance, they use the same symbol for both the tweeter and the woofer, but otherwise you'll see that it's exactly the same thing. If the split occurs inside the wooden cabinet, suddenly we call that normal wiring, but if the split occurs outside the cabinet, then we call it bi-wiring. It's a ridiculous sham. It's the same thing electrically. Also, people have to get it out of their head that for some reason the high frequencies jump up here and the low frequencies jump down here. The signal measured here is the same as the signal measured here, is the same as the signal measured here, is the same as the signal measured here. It's only after you go through the high-pass filter and the low-pass filter that there's frequency differentiation. At the moment. This is what the highs sound like. This is what the lows sound like. Combine them together and you have full range noise. So that's at least how they conceptually describe it to you. Highs and lows. But what happens if you attach the highs to the low input? That proves this is not just the highs, it's the highs and lows. The noise difference you hear is just the tweeter versus the woofer plus the crossover network. So it's an illusion that one is low frequency and one is high frequency. Both are carrying the full range signal. So let's check out what's going on internally. So this part is sometimes called the terminal cup. I've turned off the amplifier. And often these days they just mount the crossover right to the terminal cup. So now we have access to these, and I'm going to test them with probes. I have probe wires, and I can connect to the tweeter and to the woofer independently. So I have my spectrum analyzer set up, and I have the test probes perilously connected to the tweeter and woofer. If I wiggle them, they'll snap off and possibly short my amplifier, but I'm trying to be very gentle. So let's look at the spectrum analyzer. It's set from 20 to 20 kilohertz. So here's the noise signal. This is obviously the tweeter. After it goes through the high pass filter, so only the highs pass through. And this is the lows going to the woofer. Only the lows pass through. So that's tweeter and woofer. However, what if we disconnect these and instead we monitor just the highs coming in? So now we're monitoring just the high frequency input. Look at that. Full bandwidth signal. No crossover. I thought those were supposed to be only the high frequencies. That's what the brochure said. So that's malarkey. The incoming signal there, you only hear it in the highs. If I disconnect the lows, you only hear the high frequencies, but the signal itself, as you can see, is full bandwidth. And the same is true down here. Supposedly that's just the lows coming in, however the spectrum analyzer shows that it's the full range signal 20 to 20. So much for the lows and highs traveling through separate wires. That is a myth. So the concept that intermodulation distortion should be reduced when bi-wiring is based on the assumption that highs and lows are kept apart, but they're not kept apart. But just to be safe, I ran IMD tests using both multi-tone, sounds like this, and also SMPTE two-tone tests, which sound like this. And neither showed any change in intermodulation distortion. In fact, this one, the SMPTE test, showed that the bi-wired tweeter was a little worse, but I think that's really just because that last digit, that 0.006 part, varies reading to reading. So another way to think about bi-wiring not being legit, and they're truly the same thing, is that they claim that the high and the low frequencies, by keeping them separated, you don't contaminate each other, or if you want to use fancier words, there's no intermodulation distortion. But that's not true. The amplifier travels through a single wire right here to get to the outside of the box. So if highs and lows contaminate each other when they travel through the same wire, that has occurred right here. So splitting it means you have two contaminated signals then traveling through to make your music. But the music started with the highs and lows combined through a single wire, this little wire here. So that's another reason that it's sort of bogus to claim that the highs and the lows are kept separated. They aren't kept separated anywhere else. The microphone wire in the recording studio, it wasn't bi-wired. The mic preamp it led to, it wasn't bi-wired. The mixing console, the recording decks, the compressors, limiters, equalizers, processors, none of it is bi-wired. It all travels through single wires, as does the signal in your stereo system, at least right here. So this argument that keeping them separate makes them sound purer is all baloney. The only legitimate difference between single wiring and bi-wiring is that you're using a lot more wire when you buy wire. And that's why dealers like to push this myth, because they know that the customer will buy wire twice as much as they need to buy, because they fall for this myth, which is completely bogus. Don't fall for it. So the only legitimate thing you could say about it is that since you are using twice the number of strands across your living room floor, it does have a lower resistance than using a single wire. However, you could have done that simply by using dual wiring on a single speaker. Dual or double wiring accomplishes the exact same thing, and you don't need fancy binding posts on your speaker to do it. So you can't really claim that that's the real advantage to bi-wiring, because you could have done it with any speaker. I was a high-end dealer for a little over 2 decades, and pretty much all the brands I carried did indeed have dual binding posts. But you could argue they offered it for people who wanted to buy amp, not buy wire. Also, just because they have dual binding posts doesn't mean they believe in either bi-wiring or bi-amping. It just means they want to offer it for people who do think it's important, or because they want to be friendly to the dealers that want to sell extra gear to the consumers. It doesn't really say anything at all about what they themselves think. Some were very wishy-washy about it when I would corner them on the topic. One, however, 𝑺𝒆𝒄𝒓𝒆𝒕 that you see here in this image, they make some speakers that cost $250,000, by the way, although these are just a few thousand. Their attitude when I cornered them off the record was, no, we don't believe in it at all. However, we don't want to lose a single sale to any consumer that does think it's important, because the added expense to us to provide this kind of terminal cup is trivial compared to the sales that we think we'd lose. Another company I carried, Wilson Audio, they make speakers that cost $685,000. They didn't believe in bi-wiring at all. They don't talk about it in their instruction manuals. They themselves were anti-bi-wiring.